Maxwell, and this is my Lab 3 of the black hole. This lab was a two-part lab, the first purpose being to find the mass of the black hole and the time between data points in the trajectory, and the second purpose to predict the motion of the planet and the spaceship by calculating all the necessary gravitational forces. In part 1, we used the Newton's second law to calculate for the mass of the black hole, and in part 2, we used trial and error to find a possible initial velocity for the spaceship to safely leave the system by being as close to the black hole as possible. The results, according to the calculations, the approximate mass of the black hole was 15 e24 kilograms, and the possible initial velocity was calculated to be negative 4 e7, 1.8 e60 meters per second. The fundamental principles of this lab are Newton's second law and instantaneous rate of change momentum. As you can see for Newton's second law, we have change momentum equals F net times change of time. This can be manipulated to equal dp dt in this equation. The instantaneous rate of change, speed equals F parallel, and then the direction is F perpendicular. Together, they create F net as well. This is the Python code for part 1 of the experiment. The system is the star and the surroundings of the black hole and the rest of space. The initial conditions are more or less unknown, except that we know the star is orbiting counterclockwise around the black hole. And the other important details are the mass of the star and the duration, which had to be converted from 1 day into seconds for SI units. As you can see, we can find F net with this equation with the arrows. We found the F net parallel and the F net perp, and then we calculated the mass of the black hole using this equation by manipulating the force equation. These are the results for part 1. Because of the specific gravitational force of the black hole on the star expressed in elliptical orbit. The mass of the black hole was calculated to be 1.5 e to the 24 kilograms. There are possible sources of error by the approximations made in the Python program due to the fact that the mass of the black hole changes every iteration. So this mass is closer to being an average than the actual mass of the black hole. As you can see in the table below, we have F net parallel, and F net perpendicular as a magnitude. This is the Python code of part 2 of the experiment. The system is the spaceship and the surroundings of the planet and the black hole. The initial conditions of this experiment, the direction of motion from the planet in the positive y direction. Some other important details to include are the mass of the black hole, which we found in part 1, the mass of the planet, and the mass of the ship, both of which were given. There is an equation down below, which is F net equals the force of gravity of the black hole on the ship and the force of gravity of the planet on the ship. And this was indicated in the Python code for calculations. These are the results of part 2 of the experiment. The initial velocity was calculated to be, through trial and error, negative 4 e to the 7th and 1.8 e to the 6th meters per second. By this initial velocity, the spaceship would be able to leave the system without hitting the planet or getting sucked into the gravitational pull of the black hole. There are possible sources of error, including human error regarding the trial and error of inputting possible initial velocities, and discrepancies not accounted for, like the optimal angle of takeoff from the planet. As you can see from the graph to the right, the angle or the trajectory of the spaceship gets as close to the black hole as possible without getting sucked into it, and avoids getting or hitting the planet and its orbit. The orbit of the planet is a little bit longer than the time that this calculation went. It went around for 60 minutes, but the planet's orbital period is around 1.7 hours instead. So that's why it doesn't make a full orbit, which is not important because we just needed to know if the spaceship was going to make it out in time. These are the discussion questions of this lab. What does it mean? Although F net, including F net parallel and F net perp, and the rate of change of momentum do not differ mathematically, the way to solve for both requires different components. In this case, the rate of change of momentum uses velocity and mass to find momentum as a function of time. However, in this experiment, F net cannot be calculated directly without knowing the mass of the black hole, which we found in part 1. Playing around with different velocities to allow for the spaceship to enter an orbit around the black hole without crashing into the planet, I was able to find a possible speed in the x and y direction that could work. The ship speed in the x direction could have been negative 1 e to the 5th, and the ship speed in the y direction could have been 1.1 e to the 7th. As you can see from the picture below, the orbit of the spaceship is the magenta line, and the orbit of the planet is the cyan one, and the orbit of the spaceship is closer to an elliptical orbit, which is what we discovered in part 1 with the planet. But in this specific iteration, it looks like the planet's orbit is more circular, just to show the distinction of the elliptical orbit of the spaceship. Thank you for watching.